Introducing. And hello everyone, welcome to my talk on computational embeddings of DSLs. I'm Yao Zhu from the University of Hong Kong, and this is a joint work with the undergraduate intern Ukash and my advisor Bruno. Okay. Concerning computational embeddings, you may ask, what is embedding at all in terms of DSLs? Then let's take a look at classification of DSLs first. According to the book DSLs in Action, there are three kinds of DSLs: internal ones, generative ones, and embedded ones. The concrete examples are listed on the right-hand side. Unlike external ones that require external tool chains, unlike generative ones that need to generate a different language from the DSL, the embedded DSL just reuse the host language. Yeah, and somehow like libraries, it's very convenient for users to use if they are already familiar with the host language. Our computational embeddings are our novel approach to embedding a DSL. Here we take embedded DSL for region, for example. Here we have, initially we have 5 constructors here. For example, circle R represents a circular region of radius R. And outside A calculates the complement of the region A. And translate VA is to move the region A by the vector V. And we have two more set operators to calculate the union or the intersection of two regions. There are quite a few embedding techniques to embed such a simple region DSL. The most well-known two are, of course, shallow embeddings and deep embeddings. Here we use Haskell for demonstration. Here in the shallow embedding, we first define the type region. Region is a type to represent the semantic domain. Here, since the area of a region is hard to calculate, so we use the syntactic size instead. That is the number of AST nodes. Here we see that the size of circle is just 1, and the size of outside A is the size of A plus 1. It's very straightforward, and I will not explain union, intersection, and translate. Here we can see that in the shallow embedding, the semantics are directly represented by the language constructs. On the contrary, in the deep embeddings, the region is defined as an algebraic data type. So the 5 constructors only capture the syntax instead of any semantics. If you want to give a semantics, here we have to define a function like size by pattern matching. Here we pattern match all of the 5 constructors, and the definition are very similar to the shallow one. Yeah. And what's the benefit of shallow embeddings, for example? Now we come to the issue of linguistic reuse. Linguistic reuse is a very important concern of embedded domain-specific languages, because it means if you have linguistic reuse, you can almost reuse all of the infrastructure in the host language and inherit most of the optimization. For example, here we take let sharing, for example. Here, since it's in the shallow embedding, the region type is already defined as int. That is the syntactic size here. So the variable shared is of type int. And since we use let in Haskell, so the shared variable won't be calculated twice in the let body. So as a result, we avoid duplicate computation, and the evaluation of this program terminates instantly. On the contrary, in the deep embeddings, the type region is defined as algebraic data type. So shared is actually a AST. After the AST is generated, is actually duplicated twice in the subtree of the nodes. So after this, if we want to call a semantic interpretation like size, actually the shared will be calculated twice. And since the function goal is recursively, it leaves a lot of duplicate computation, and the program will be very slow. In other words, in the deep embedding, the let sharing only exists in the syntactic phase, but it is lost in the semantic phase. Another problem is called the expression problem. As the DSL involves, we may want to add more language constructs. Here, for example, we want to add 3 new constructs like the universal region, the empty region, and the scaling operator. In the shallow embedding, it's very easy. We just need to define 3 more functions. These functions just represent the semantics directly. But in the deep embedding, it's very difficult because the algebraic data type is closed. So you want to extend it, you have to rewrite it. And also you need to modify all of the pattern matching functions that to add new cases. On the contrary, to add a semantic interpretation in the deep embedding is very easy. You just need to define a new function by pattern matching like this. For example, the contains is to check if a pointer resides in a region. For example, circle R contains P if and only if P dot X squared plus P dot Y squared is less than or equal to R squared, and etc. It's very easy in the deep embedding, but it's very awkward to add a new semantic interpretation in the shallow embedding because the semantic domain is already fixed after you define the type region. So we need to modify the definition of region and all of the language constructs to map them to a new semantic domain. So this tension between 2 dimensions is well known, called the expression problem by Professor Wadler. Although this problem is well known and many modern embeddings like text-final and polymorphic embeddings have addressed this problem, but they have a significant difficulty when they handling dependencies. What's a dependency? Here, let's take an example like is univ and is empty. When you write domain-specific optimizations, you may want to check if a region is universal. Then you can just simplify it into a single univ constructor, right? And to write such a function is tricky because, for example, here, if any region outside the empty region, then it's a universal region, right? On the 3rd line here. And it's actually a mutual recursively defined functions here because if you want to check if a region is empty, you also need to call its univ to check if the nested region A in the outside case, if it's univ. Then the mutual recursion is very hard to handle. Actually, the definition is straightforward in the deep embedding. But the tactless final and polymorphic embeddings are more like the shallow embedding that we have to use a non-modular workaround. Here, we define the region type as a pair. That the left-hand side is represent is univ and right side is empty. And if we want to recursively call the 2 interpretations, we need to use the Haskell function first and second here to access them. And it is non-modular because if the 2 interpretations are now coupled tightly. If you want to add a 3rd interpretation, you need to rewrite them wholly, and of course, you need to rewrite these language constructs. Due to the importance of dependencies, we extend the expression problem with the third dimension. We call it dependencies here in the table. Although polymorphic embeddings and tactless final can handle the original two dimensions, but it cannot handle the third dimension very naturally or modularly. And that's why we want to introduce our new embedding called compositional embedding. As Svenningsson and Axelsson said, the holy grail is to combine the advantages of shallow and deep in a single implementation. Then let's go to our compositional embedding. Our compositional embeddings are based on our recent work on compositional programming. That's a statically typed modular paradigm and is implemented by our language CP. So our code are all written in CP. I will not do a tutorial on our language, so I will just introduce the features we use in this talk. Here, in the since CP is statically typed, we will first define an interface that declare all of the 5 constructors. So the capitalized ones are constructors as before, and the interesting thing is that the type parameter, we call it sort, and all of the constructors will return sort as seen in the code. And the sort is abstract here, but it can be instantiated to different types to map to different semantic domains. Here, we instantiate the sort to size. The size type is defined as a record, has a size, has a label size, and the field type is int. And we will implement such an interface using a trait. Traits are the basic unit of code reuse in CP. You can just regard it as a class if you are familiar with OOP. And the definition of SC is very like the pattern matching one in Haskell. And we call such a syntax method patterns. And let's go back to the issue of linguistic reuse. So in the CP, the compositional embeddings, the let sharing is also available. Linguistic reuse is automatically achieved in our compositional embeddings, just like the shallow embedding. So here, the shared won't be calculated twice because of the let sharing in the host language. And the evaluation of the whole program will terminate instantly. To add new constructs and interpretations, we can refer to this code. And actually, you don't need to read the Greek code because it's just translated from the previous code. You can just focus on the sketch that we first define an interface that contains 3 new constructors, and we can still implement it using a new trait SZ prime. And to add a new interpretation, we just as deep embedding, we define a new trait, implemented the interface with the sort, instantiated to a different type. Here, the different type is eval instead of size previously. And we implement them using method patterns as well. And how to combine the interface and the interpretations? To combine the interfaces, we use the intersection type. To compose the interpretations, it can be difficult, but we managed to make it using nested trait composition. Let's take a closer look at the trait composition here. Here, the comma denotes the merge operator. And to make the precedence clear, we add redundant parentheses on the second line. We visualize the conversation in the figure below, and you can see that the trait conversation is called nested because not only the constructors are merged, but also the semantics inside inside the same constructor are merged. To take a concrete example, here not only the circle in the SZ and the unif in the SZ prime are merged, but also the contains in circle in eval and the size in circle in SZ are merged, as shown like in the shapes, the final result. Actually, the language constructs and their semantics form a two-level hierarchy of traits, and this conversation of the whole hierarchy can be traced back to family polymorphism. Our nested trait conversation is based on our theoretical work on distributive subtyping for disjoint intersection types, but that's a different story. I won't dive into that in this talk. And how does CP handle dependencies? We introduce a novel way to dependency injection, like this. Here we can see the interface are instantiated by two types, separated by the fat arrow. We can roughly call the isEmpty an input and the isUnif as an output. The input, the isEmpty, is actually not implemented in this trait, but we assume they are present. And the static type checker of CP will later check if this trait check unif is later merged with another trait implementing the isEmpty. Actually, that trait is just check empty, right? We will later merge it, but hold on, let's explain it a little bit more. And we can see that the isEmpty and isUnif can call each other, and it's our way to implement mutual recursion here, and that's totally type safe. Okay. Here is a detailed comparison of existing embeddings in the literature with our conversational embeddings. You can see that some cells are marked half circle for some reason. We explain it below the table, but maybe there is not enough time to look at the table in detail. But we want to say that conversational embeddings are the most versatile one among the embeddings here. So far, we used a very small DSL, the region DSL. You may wonder if our approach can scale to larger DSLs. So now we introduce a larger DSL called EXT. We will not, since time is limited, we will not dive into the syntax or the design of EXT, but there is a figure that the left-hand side EXT code can be rendered as a document on the right-hand side. The implementation can be found in plgrant.org if you want to visit it. And we have 3 case studies can also be found in that website. The first case study, the application is Minipedia. It's a mini document repository for cities and states. It demonstrates the extensibility of our language because, as shown in the figure on the right-hand side, we have a lot of components in this language, and some of the components are provided in a library. Oftentimes, we cannot access a library to modify the code in a library. So it's very important to achieve the independent extensibility here. And the extensibility are two-dimensional, of course. We can extend the language constructs like this, and we can extend the backends. For example, LaTeX and HTML, we can extend more backends if you want. And the second application is fractals. It shows that the general purpose computation and the linguistic reuse are both available in our EST language. And the last application is about customizable charts. It demonstrates our approach to delegation in contrast to the traditional OOP design patterns. Last but not least, the key features of compositional embeddings can also be encoded in Haskell and Scala. You can refer to these two papers for details, but note that it comes with a cost of a lot of boilerplate code. That's why we want to integrate it into the language level instead of to use it as a design pattern. If you are interested, you can read our paper for more stuff. For example, our novel way to support nested pattern matching, a detailed comparison, and the design of EST. You can also find the complete Haskell code showing why the tagless final embedding are not so satisfying. And that's all for my talk. Thank you for your attention, and feel free to ask me questions.
No.
I think it is. Yeah.
Cool. Do we have any questions? Okay.
So can you talk a bit about ideas you might have for like extending the languages to avoid all this boilerplate code to get the embeddings in Scala and Haskell?
Oh, yeah. To put it simply, in Haskell, the problem is how to handle the dependencies, right? So in the Haskell, we can use type classes to encode the type index record and to make use of the resolution of type classes to select the interpretation automatically and avoid the first, second explicit projections and the non-modularity in Haskell code. And for Scala, the idea is called object algebras, if you heard about it. There is a generalized one, generalized object algebras that also the main problem is to how to compose multiple dependencies and to modularly and to use them conveniently. And the generalized object algebras using some meta programming techniques to generate the composing code for every two interpretations, and you can refer to the details in these two papers. Yeah.
So do you know about OCaml's polymorphic variants?
Yeah, I know.
Okay, so I see you compare your approach with Haskell and Scala, but how does it compare with approaches based on polymorphic variants? Would you be able to say a bit about that?
Oh, yeah. Let me think about it. Since polymorphic variants are, you can add whatever branches cases dynamically in the polymorphic variants. So I believe the same as the footnote one. The exhaustive pattern matching cannot be naturally achieved in polymorphic variants, I believe. But we did not actually look into this comparison because polymorphic variants is not so commonly used in the embedding techniques. But it would be very interesting questions that we want to look into later in the future. Yeah. Thank you for your question. Yeah.
Thank you for your talk. I was wondering, usually when you have a language, you define like evaluation functions or interpreter that map a program to a particular value. And value domains can also differ among languages or language fragments. So I was wondering, is this approach suitable to compose languages or language fragments that have different value domains?
Let me see. Yeah, I think we can because the semantic domain is reflected in the sort we use here. For example, the sort is LaTeX and HTML. We regard it as different semantic domains, that they are using the same language constructs, right? The 5 or 7 or 8, maybe at last it becomes 8 constructors. And they can be composed using the nested trait compositions because semantics are nested inside the constructors. And we nested in the constructors, we can compose different semantic domains. I don't know if that's your question.
Yeah, it hints a bit at the right direction, but I think I need to study your approach more to fully understand it.
Yeah,
But thanks you for the intuition.
Yeah, thank you for your question. Yeah.
Okay, thank you.